Okay, so it should be recording, and then I'll upload them afterwards. The first parts of it, I guess, won't be a major problem to catch up on that. So we'll go over the qualitative approaches, sort of what is thresholding, which is sort of the easiest way of doing this segmentation, and how does that work? How do we look at different images? What are the different kind of approaches we have for looking at this and analyzing it? A little bit about the implementation, and then morphology, contouring, mask creation as sort of the end. And that might actually leak over into the next lecture, depending on how much time we have. So for the applications of this, there's not every image, but most of the images you're looking at are going to be quite important to segment, to divide up into different groups. And so, the simplest case is where you really have two-phase materials, where you're looking at like bone and air or cells and background, and you're going to try to sort of classify that into two different materials. And so the easiest is where you just have one channel, as we call it, so just one intensity value. But of course, there are lots of images that have more values there, and how do you incorporate that? Then sort of multiple phase materials, and so this is where you have like soft tissue, hard tissue, and then air. And so you now have three different phases that you're trying to segment, and what do you need to be sort of concerned with when you do that, so that you don't make mistakes, because you run into new problems when you have multiple phases that you're trying to segment. Sort of how do you go about filling holes in materials? We'll then have an example about segmenting fossils and attempting to segment the cortex in the brain. So this is a brain image we have from phase contrast imaging, and to segment the cortex region out of this is quite a challenging task. So there's lots of references for this. Again, the book that we've covered before talks about some of these ideas in a very sort of general way. We then have sort of the models and machine learning approach. There's a really good talk on YouTube from Stripe. I don't know if any of you are familiar with that company. It's a company that does payment processing, and they, of course, spend a huge amount of time trying to automatically identify fraudulent payments from good payments, and that has a lot of overlap with the things that we're doing here. And so we're looking at images, and we're trying to identify two different phases, and they look at payments and try to identify good payments from bad payments. And so they have to come up with different criteria, and they have to come up with a good way of assessing how well they've identified sort of correct transactions or not. And that's the same tool set that we use for this. And so this is where that sort of overlap with machine learning becomes quite strong. So when we look at sort of why do we do these imaging experiments in the first place, sort of the first or main topic there is the exploratory analysis. And so we have samples, and we really want to see inside them. So you have a cell, and you want to know what's inside of it. So you want to be able to qualitatively say that there's these different sort of organelles inside of it. They have this spatial relationship. They seem to be changing. You don't really have prior knowledge or expectations. You're simply trying to understand your sample better. When you move beyond this, and so this is sort of the exploratory approach to a more sort of scientific approach, I guess as we'll call it, you want to test some sort of hypothesis. And so you want to use the imaging data that you have to support this hypothesis that you're testing. And so it's sort of a quantitative assessment coupled with statistical analysis that we'll get into later. And so some of the questions that might come up are sort of, if you're looking at a foam or a bread, does the temperature you cook the bread at affect the bubble size? And so this is something where you sort of have a hypothesis that it does or does not, and then you need to measure the bubble size in all of these images and be able to compare bread at high temperature and bread at low temperature to make this assessment. Similarly, if you're trying to look in sort of the link between genes and bones, you want to know, is this gene important for cell shape or mechanosensation inside of the bone? And so to assess that, what you need to do is you need to sort of have a mouse or some animal that has this gene turned on, and then another one where this gene is turned off. And then you compare the cell shape between these two different samples. But you need to have some metric for comparing the cell shape to show that there's actually a difference, and that the difference is large enough to be considered significant. And then there's other questions with, does granule shape affect battery life expectancy? And so if you have different shaped granules inside of your battery, does it change how fast you can load it or how many cycles you can put the battery through? And so what we want to look at is this image of the cell, and what we get out of our machine is sort of an image like this. And so how do we get closer to this sort of labeled image where we know this is the capsule, this is the nucleus, this is all the other components inside it, and that's what this lecture focuses on. And so we look at sort of to test a hypothesis, and so we perform an experiment to see sort of how big the cells inside of the tissue are. And so we do these measurements, we end up with 56 gigabytes of data for every sample. We then last time learned about the filtering and pre-processing. It takes a long time. You do these nice non-local k-means or other things. But you still have 56 gigabytes of data. You haven't reduced the amount of information at all. You've simply made it a little bit cleaner. And so how do you go on to the next step? And so what we want, and I think this part is quite important, is a single number. And so when you're doing statistical analysis, you need to have a single number that you're examining. So you can't say cell shape. You need to say something, the number of cells, the average stretch of a cell. So that's the case where the cell stretch is defined as sort of the longest axis compared to the shortest axis, the volume variability, the volume fraction. So there's a lot of different numbers you can come up with. But ultimately, to do any of these analyses, you need to reduce this data set down to a single number that describes your sample. Because anything other than a number, you can't compare easily. And so sort of why do we perform the segmentation in the first place? And there's two different types of segmentations that we perform. But it's really to take this data and to simplify it as much as possible so that we know, so we can take from this image information about what's classified as each different group. And that's where it's really important to have sort of a good approach to analyzing it. And one of the things that I think is quite important is sort of this Occam's razor idea, and that the simplest solution is usually the right one. And so you'll see lots of very, very complicated approaches to analyzing problems. And you can use genetic algorithms and Bayesian models to segment an image. But if it's not necessary, you're adding a lot of additional complication that might not be actually improving your result. And so with this, it's important to say, if you require, 20 different steps or genetic algorithms in order to identify bone from air, then maybe your image isn't good enough to actually do that. And you just need a complicated approach because you're trying to do something that's fundamentally not possible with the image. There are, of course, many tasks where you need to have such a complicated approach. If you're trying to identify if this is a picture of a cat or a dog, then that's probably not a problem you can do with a simple threshold. You need a more complicated analysis. But if you're trying to segment things, or if you're trying to look at which part of the image is bone or which part of the image corresponds to cancer, then the more complicated approach you have, the more sort of fragile your tools are and the less likely it is to be reliable. This is also cases where you need much, much more information to make it work well. And so when you're looking at sort of these machine learning or deep learning approaches for identifying cats from dogs, they typically look at millions of images in order to test this approach. And so if you don't have millions of images, you can't use such complicated methods reliably because you have sort of this risk of overfitting, which is something we'll talk about later. So to kind of go over the filtering and enhancement very quickly. So with this, we sort of had this idea that there's this noise process that's added to an otherwise clean imaging data set. So we sort of have our measured data, which is the sample plus some noise. And we don't really know what this noise is. We understand a little bit about where it comes from or where it can possibly come from, as we covered last time. And sort of the perfect filter would be something that we can apply to our measurement, and we would get out the sample. So there should be measurement to fix that. And so it sort of gives us out what we want to have. And when we apply it to the noise, we get nothing out. And so the filter here would sort of keep our image perfectly intact, not do any damage to the original image, but it would get rid of all of the noise. Oh, sorry, this is the right one. So if you have your original image, you get out just the sample at the end. What most filters end up doing, so sort of in a really good case, is you have your measured data here, and you apply your filter, and you end up with sort of 90% of what's really coming from your sample, and maybe 10% of what the noise was. And so you reduce the noise a lot, and you reduce the image a little bit, or the content of the image a little bit. If you have a really bad filter, or you choose really bad parameters, what you end up doing is you end up having sort of a huge amount of your image information lost, and your noise gets amplified. And so what we covered last time, if you sort of have a slightly noisy image, and you apply some of this edge enhancement or high pass filters, then you can end up easily doing this to your image because the noise has much higher frequency components than the image itself, and so you end up amplifying the noise without doing anything to the image. And so qualitative metrics is sort of what is common, or what was common in this area up until better approaches came out. And so you take this image that looks out and you sort of describe it qualitatively. And so you say there's many little cilia on the surface, there's a long curly flagellum, elongated nuclear structure, other sort of descriptions like this. And this is helpful, of course, for looking at the images, but it makes it very difficult to compare them. And you could even do sort of morphometrics in a quasi-qualitative way, where you could print it out on equal weight paper, and then you could cut it out and weigh it, and that would tell you the area of whatever feature you were looking at. And I guess that's quasi-quantitative, but it's not really scalable, because if you're not very good at cutting with scissors, then it doesn't give you a very reliable result. So now when we look at the segmentation approaches, this fits very well with the sort of ideas we covered in the first lecture. And so we have sort of the image analysis approach, and we have the experimentalist, the computer vision, and sort of the deep learning approaches all come together. And what we've covered last time with this image enhancement is very much the experimentalist approach. And so the experimentalist approach is really this model-based, problem-driven, top-down, and it's based on some sort of reality. The other approaches, which we'll discuss today, are really the machine learning approaches. And so this is where you say you sort of have a goal that you're trying to reach, and you build up your model to reach this goal, rather than saying you understand the process that's generating your image, and you use this understanding to analyze what you're looking for inside of it. And so we'll cover sort of what those two techniques imply, and how you apply them to certain problems. So the model-based analysis, which we'll cover at the beginning, is really the physicists, or sort of the more engineering approach that we have, where you have some sort of impulse or excitation. You're looking at a characteristic of your sample, and so this might be, the density, the amount of fluorescence probe in a certain area, any number of other factors. You then have this response in your detection system. And so there's many different imaging modalities, but basically the equations underneath are the same. And so you have your measured signal, which is a function of your stimulus and your sample. And you're trying to sort of understand this sample better. And this is where we can see, sort of in a very simple setup, where you have your beam, your sample, and your detector. Your system is sort of just combining your beam and your sample. And so it's just a multiplication that we have, because where the beam hits is where you're likely to have response. Your stimulus is this profile of your beam, and the system is sort of this absorption coefficient. And so the absorption coefficient is then the measured result divided by the beam profile. And so here, where we have a constant beam profile, we have a sample that looks like this. We have an output that looks exactly what we'd expect it to look like. So there's really nothing happening in our system, and it's quite straightforward. So all that happens is that this becomes slightly darker because we're measuring it. This is an absorption, and this is then what we see on our detector. Of course, when this is non-uniform, which is very frequently when we do this set of experiments, then the beam profile is not flat anymore. So if you have sort of a gradient profile here, your sample doesn't change, but what you get out on your detector looks very different. Similarly, if you sort of have a spot-shaped profile, then again, the output on your detector is very different. And so this is one of the things that's sort of challenging to try to correct for, because you have values here that don't correspond directly with what's in your sample, and you need to somehow find a way of identifying the interesting features, even though you have this sort of noise or this background that's difficult to remove. So when we look at sort of absorption imaging in more detail, we have, for all of you who've taken sort of another imaging course before, this idea of sort of the Beer Lambert Law, where you have some absorption coefficient. So this applies to X-ray, ultrasound, optics. It sometimes have different names in different fields, but more or less it's the same idea, and it's the same equation that drives it. And so that you have this intensity at your detector, the intensity at your source or your stimulus, and then this that describes your sample. And so, the thicker your sample is, the more it's going to absorb in sort of an exponential way. And the relationship is that, different components will have a different alpha value. And so in X-rays, this is then strongly connected to the atomic number or the density you have in a certain region. And with ultrasound, this is then related to the it's related to sort of the material properties you have and the spacing between the atoms you have in your lattice. And so you're looking at different sort of properties in different materials when you do this analysis. And so basically what you end up with is this formula where you have a spatially varying alpha parameter there, and you're trying to segment out sort of this alpha value. And so you have all of this in, and you want to reconstruct what's the alpha value you're looking at. And so, if you see, this case will have more than two components, and they're distinguishable sort of by their values. And so you sort of have a low density, a medium density, and a high density thing here. And even though the alpha scale sort of goes between 0 and 2, the range we have in the intensity at the output is sort of stretched out because of this exponential function. And so one of the first things we need to do is correct for that so that this linear scale here is also linear there. Because if you have exponential scales and you try to apply linear analysis to it, it doesn't work very well. And so we have to transform this plot into sort of this probability density function of the alpha components themselves, which then is sort of linear distributed and much easier to sort of define hard cutoffs between them. So in sort of looking where does the segmentation get us, it sort of takes this decimal value or sort of this more complicated input that we have, and it simplifies it down to a single discrete value. And so with the intensity images like we have here, it's simply this intensity that we're trying to convert into, or this absorption that we're trying to convert into sort of an identification of what material it is. But in a red, green, and blue image, it's then taking this vector that we have of 3 different colors and just assigning it to a phase that it belongs to. And so when we look at sort of the data that we have in our image, we go from this 56 gigabytes to sort of from a 32-bit representation to a 1-bit representation. So at each point, we have 1 bit of information saying if it belongs to this phase or not. And so it's a massive reduction in the amount of data we have to describe our system. It's still far away from sort of having a single number for this data set, but you're much closer along that path. And you've gotten rid of a lot of the unnecessary information for performing further analysis. So applying a threshold to the image, and so a threshold is sort of the easiest way to do this segmentation, and probably something you've seen or already kind of familiar with before. And so you have your image here, which is really this function of x and y, and you have different intensity values. And so this is the sort of intensity at each point shown as an image. We can also show this as sort of a probability density function or a histogram. And so what this shows us is the intensity distribution for the entire image. And so I assume most of you have seen histograms before. So you're familiar with this a bit. So this then corresponds to, these values here refer to sort of these brighter values in the image. These darker values here refer to these values in the background. So it's quite straightforward. And so these are sort of the two representations that we have from this image that we use to try to threshold it. So we then take this, and you can apply a threshold. So this would be a very simple one where you say, if it's less than 0.5, it's 0. If it's greater than 0.5, it's 1. And so here we are able to segment out sort of the cross quite well, so that the cross is part of the output image and the background is no longer there. And so we end up with a distribution, a probability density function that reflects that as well. We can also sort of apply varying thresholds. And so you can see if you apply a threshold of 0.2 versus a threshold of 1, you sort of dramatically change what you segment out of your image. And so, this one, which one is the best depends a lot on what sort of things you're trying to analyze in your image. And that's sort of what we'll go into a little bit in the next part. But you see here, this image is perfect, but then when you go a little bit higher, you're missing a lot of these pixels. Yeah?
But how do I find out? I mean, in this case, I know that it's going to be a cross, so I know where to put my threshold.
Yeah.
But how would I usually do it? I mean, I don't know what I expect, so how can I say what it is?
Yeah, if you have no idea what you expect, you can't do a threshold.
Oh.
It simply doesn't make, the computer can't understand the data better than you do, or at least not yet. So you need to have some idea of what you're looking for in your image. And so this model-based approach is really where you say this 0.7 or this 0.8 refers to the absorption coefficient of bone or the absorption coefficient of bread. And I choose that value based on my physical understanding of the material, and the image then matches well with what I'd expect to see. But yeah, we'll go into if you don't have that, or what we see is that a lot of these noise processes or these imaging things that happen make it very difficult to assign a single value to what you're trying to extract. Because as soon as you don't have a good detector, as soon as your machine, or as soon as your illumination isn't constant and you can't correct for it, as soon as all of these sort of real world factors come in, the ability to say it's 0.7 because I looked it up in a table and that's what the absorption coefficient should be is no longer realistic. But yeah, this is one of the major challenges that you have with this kind of imaging. And if you really have no idea what to expect, it's hard to check your results. So now with something like cells, so we could perform the same sort of analysis with an image of cells. And so we have this image here where there's some cells and some dust in the background. And we can show it there. And then we can show an intensity graph here. And sort of the idea is that the field is illuminated by white light of nearly uniform brightness. So we don't really have any problem with the beam profile. There doesn't appear to be a gradient or anything that's in the image. And we know that cells absorb light, causing darker regions to appear in the image. So these dots here are because the cells are blocking the light going through. The problem is there's lots of other things that absorb light as well, like dust or sort of random fluctuations in the detector. And so how do we sort of find the cells in this image reliably? And so we can try different threshold values where if you go too low, so if you decide sort of right here defines a cell, then you end up with things that are definitely cells, but you probably don't have all of the cells in the image. If you sort of go too high, then you end up with a huge number of things which are certainly not cells. And if you're somewhere sort of in between, then you have this good number. And so with this, you could try to calculate what you'd expect the intensity or the absorption of a normal cell to be, and use that as sort of a guide for picking your number. You could also say that there's supposed to be so many cells in the sample, and use that as the guide for adapting this, because sort of the fluctuation you could expect for an object that is a cell is probably anywhere between here and here. And so your physical model doesn't bring you all the way there. And so you need to sort of bring in other information in order to do that more accurately. But of course, there's other image types that we have. And so some approaches, X-ray scattering and grain mapping approaches will give you sort of a vector or a tensor at each point in your image. And so this means you don't simply have an intensity, you have sort of an orientation. And so now you have an image that you sort of can't even easily visualize, because at each point you don't just have a brightness or a color, you actually have an orientation. And so you can try to show this through sort of an orientation histogram where you see what the distribution of orientations are. That doesn't help you too much. And then what you can apply is you can apply sort of a threshold in the same way before, where instead of looking at simply one channel, you look at both of the channels. And so you look at sort of the X direction and the Y direction, and you apply a threshold to that. And so then you can take out sort of this region, if this was the region of interest for you, because that's then oriented in the upper right direction, and that then gives you this grayscale or this black and white image out. So you go from this 2 channels of information to a single bit. So you get the same result out, but your input image is much more complicated in this case. But you can also sort of do more complicated thresholds because you're not limited to sort of a single cutoff. With this, you could say, anything that's going left or right is what I want to keep in the image, because this is sort of maybe a flow image, and you want to find the points where the flow is sort of going perfectly perpendicular to the y-axis. So that would give you these points in the image that you could then analyze further and use for some other kind of analysis. You can again apply even more complicated things where you sort of have acceptance angles, where you say that anything that's in these sort of different range of directions is what you want to keep. So the point of this is that you can, as your data sets get more complicated, the sort of criteria you can apply for a threshold can get massively more difficult to compute and more difficult to define carefully, but fundamentally your output image is always going to be something that's black and white or has very few different phases inside of it, and that's the sort of result you're looking at. So now to kind of switch over to this machine learning approach. And so this is where we sort of don't necessarily understand the physical process or the connection between the physical process and what we're trying to do is tenuous enough that we can't exactly say the absorption coefficient should be 0.5 because that's what the table says. And so what we'll use for the example here is just a hypothetical image. We'll then move on to a real image where we have a ring. And so here, this is what we know it's supposed to be. So we've taken a ring that we want to image, and that's what it looks like. And the image that comes out of our detector then looks something like this. And so it's very noisy. Our eyes can sort of see that there's supposed to be a ring there. But if you were to try to just apply a threshold because anything above 200 should be a ring, you would struggle a lot. And so I think in the next slide we show, so if you try to apply a threshold, that looks then nothing like the ring that we're trying to look at. And so what we have here, you see that there's some bright values there, but you can see the ring fairly clearly. And so now what we want to do is we want to identify from the image which pixels belong to the foreground and which pixels belong to the background. And so we've defined the ground truth here, which is where we say the ring is sort of the foreground, and that's light blue, and the background is pink. And so we want to classify this image based on the values that we have inside there into this foreground and background approach. And so how do we sort of start to quantify this? And so we have these standard sort of terms that we use where you have true positive, true negative, false positive, and false negative. And I assume, has everyone heard of this idea before at least? So the idea with the true positives are sort of the things that are in the ring that your algorithm or your approach correctly identified as being inside the ring. So in the ring that are classified as foreground. True negative are values that are outside of the ring that are classified as background. False positives are values that are outside of the ring that are classified as foreground. And false negatives are values in the ring that are classified as background. And so we have sort of our first simple classification, which is using a very basic threshold. And then we are able to assign all of the pixels in our image to one of the following categories. And so we see here, our true positives are here. So the places we matched where the ring is well show up here. The false positives are here. So these are all the points that we thought were in the ring based on our threshold, that in fact were not. The true negatives were here, and the false negatives are there. And so now we've come up with these 4 different groups where we can assign the thresholds that we got out to sort of their correctness, because there's multiple ways they can be wrong. And so now what we can see is we can try a number of different threshold values, so ranging from sort of 0.3 to 0.7, and then we can count the number of true positives, true negatives, false positives, and false negatives in each case. And so what we see on this graph is how those values change as we change the threshold value. And so here we see at 0, we get sort of everything's true positive. So we have a huge number of true positives and a huge number of false positives, because we basically say everything's inside of the ring. And as we start to increase this value, the false positive rate goes down, and the true positive rate goes down a little bit afterwards. And so there's a number of different sort of points which might be optimum here. And so from this graph alone, or actually any of these graphs alone, you can't say what the best value is. All you're doing here is sort of providing a way of assessing what results you get out of your image. And so if your goal here is to make sure you always identify a ring and that you never miss a ring that comes up, but it's okay if you identify things that aren't rings as rings, then it's perfectly fine to be here. And you wouldn't want to be here, because here you see you're already missing a large number of things that are supposed to be rings that you're not identifying correctly. And of course, for the other scenario where you only want to say it's a ring if you're completely 100% sure it's a ring, and for things that might be rings, you want to put them as sort of a false or classify them as background, then it makes much more sense to be over here. And so this sort of doesn't give us the final answer, and the other curves that we talk about afterwards don't either. They simply give us a tool for knowing how well this threshold is able to classify our image. And so what we can build off from this as a precision and recall are these terms you've heard of before from the statistical sense. Okay, and it's good that we're going over this. The formulas aren't really important to know, but they're also called specificity and sensitivity. And so they're sort of the standard terms that are used to evaluate these models, where you then calculate the sensitivity as being the true positives over the true positives plus the false negatives, and the precision as being the true positives over the true positives plus the false positives. And so what we end up with for this curve is this thing called an ROC curve. And so this actually comes from communication science, where it was developed, I think, in World War II, where they were trying to detect objects in battlefield using radar. And so that's sort of the same kind of problem that we have here, where you have this image and you're trying to identify, is this a tank or is this not a tank? And so they came up with these curves as a way for describing how accurately they could assess if they were seeing a tank or not, so that you could then decide which point on this curve you want to be at so that you accurately identify the things you're looking for. Because if you're waiting for a troop, if you think it might be a tank and you need to prepare for it and it doesn't cost you very much to prepare for it, then you want to be sort of very high on this true positive scale, and having some false positives isn't really a problem. And so you want your recall to be 100. And if it takes you a huge amount of effort to prepare for a tank and false alarms sort of demotivate your troops and make it very difficult for you to sort of fight war, then you want to be very high on this precision scale. And so these sort of give you 2 different components you can focus on to try to assess. And so what we see from this curve is that as we change the threshold value, we sort of draw a line along here where we see the precision on the y-axis and the recall on the x-axis. And then what we have in this upper right corner is perfection. And so if you had a perfect system that was able to identify always when you had sort of your ring or not your ring, it would be up here. And so that would be sort of 100% recall and 100% precision. What we can now do, which is where I think the last lecture becomes very helpful, is that we have these different approaches we learned about in the last lecture, like median filters, like Gaussian filters, like non-local k-means. And one approach you can use is to do the filter and see if your image looks better. But that's not very quantitative, and that doesn't help you sort of get to your final result. What we can do now with this understanding of sort of the ROC curve is that we can take each of these different filters, apply it to our image, and then calculate the ROC curve afterwards. And so what we see here is this is sort of the normal image where we have 3 different threshold values. This has been a Gaussian filtered image, and this has been a median filtered image. And so we can now plot all of these curves, taking a number of different threshold values, and compare them. And so looking at these curves, which filter performed best?
The blue median seems to get the closest to the ideal point.
Yeah. So that's one way of assessing it?
Although, if you look at the results visually.
Yeah. So the results visually aren't always as telling. Yeah, actually this should have one. And so what's another way of assessing it? Yeah.
Well, if you say that your focus has to be on recall, then the green one should be better. So you can put focus on different things.
Right.
If it's about precision, it's also the green one.
Yeah.
You're not interested in recall.
So the median gives you more balance between the two, let's say, but it's not necessarily ideal depends on your situation.
So what we'll see is that a lot of times when you perform these filters, you'll get curves where there isn't one that's always on top always. You'll get curves that are very different. And so how do you go about comparing them well? And so the usual approach that you take is sort of this area under the curve. And so the curve that has the most area under it is the best classifier, or is giving you the best results. Because you might have a curve like this where there's one point that's really close to there, but everything else doesn't work well. And that means that it's very rare that you get something like that. But that means that you would have one exact threshold that happened to work perfectly. But if you change that threshold a little bit, or if your image has a tiny bit of noise in it, then you're away from this point, and it's not helping you. And so this gives you an idea of sort of how well your system performs on a whole. And of course, if you're making sort of a medical device, then they say you have to be in sort of the 90% precision range or 99% precision range, and then that really fixes what your recall is. So you don't have this whole curve anymore. You simply have a section of this curve because you know that you're only allowed to use values above 0.8. And so the fact that you have a really high recall at 0.5 precision is meaningless because you can never have 0.5 precision. You have to always have something above 80. And so that's where these sort of curves can be very helpful, because looking at the images, it's hard to say which one performs better. So looking at the median, you might say that this didn't do very well because it sort of fills in that hole in the middle, and that doesn't look to me like a ring anymore. And that's true, but the criteria is sort of subjective, because maybe it's more important that the ring is circular or that the ring is sort of, a circle. And the fact that the middle's filled in isn't a problem. And so if that is the case, where the middle needs to be empty, then you can sort of weight those values differently. But ultimately, this gives you a very sort of unbiased approach for counting pixels and assessing how well your classification worked on your image. So we also have graphs with true positive rate and false positive rate. And so depending on what field you come from, this might be a curve you're more familiar with. And so here you have sort of on the x-axis the false positive rate, and on the y-axis the true positive rate. So the perfect point is then in the upper left for this image. And what's nice about this one is that you can see where random guessing comes in. And so here random guessing is sort of along this purple line. And so this means if you just flip a coin. So if you don't look at your image at all, and at every point in your image you just randomly say if it belongs to foreground or background, that was what assessment you could get. And so where that really is then helpful is when you're looking, if you're ever below this curve, that means you're doing useless things to your image. And the higher you are above this curve, the better. And so with this one, we can see sort of here that the median performs best there. The Gaussian performs a little bit better in this range, and then they sort of all match up at this side. Cool. So we have examples here for evaluating models that you can look at on your own if you're interested, where they sort of have this, I think this is more detail on sort of how you actually implement, and this is what Stripe did for it, their analysis for credit card fraud. And so this then goes into more detail on some of the statistical things, and it takes sort of a fairly easy to use example where you can follow along. Cool. So now we can look at sort of a more practical example, or I guess we can take a break now and then come back and look at the more practical example and the rest of it. Are there any questions over what we've done so far? Okay, good. So yeah, we have a 5-minute break.